An aluminum shaft with a constant diameter of 50 mm is loaded by torques applied to gears attached to it as shown in the figure. Using modulus of rigidity as 28 GPa determine the angle of twist of gear D relative to the gear A. Here a shaft is fixed with the different gears A, B, C and D, and here the torque applied on the gears gear A is 600 Nm and B is 900 Nm, and torque on C is 1100 Nm and torque on D is 800 Nm. So here we will have to find out the angle of twist between A and D, that is the total angle of twist of the shaft. Here first we will have to find out the torque variation between A and D. So here draw a torque variation diagram. First consider a zero line. So this is a reference line. Here now consider the anti-clockwise is a anti-clockwise torque is a negative value, and for clockwise direction torque is negative is positive value. Here 600 Newton meter is anti-clockwise, so that draw a line down to the below the reference line. So it is 600 Newton meter. Until the B there is no change in torque. So here it is position A. Until the B there is no change in torque, and at the B there is a 900 meter which is applying clockwise direction, so that it is positive. Now draw a line above the reference line. So use 300 Newton meter here. So this is the reference point B. Now till the point C there is no change in torque, and here at the C there is a 1100 Newton meter anti-clockwise torque. Now here it is equal to 800 Newton meter. Now till the D there is no change in torque, and here at the D there is a positive, or there is a clockwise 800 Newton meter, so that so it is negative, and it is negative and it is positive. So these are this is the variation of the torque from A to D. So the portion AB is subjected to a twisting moment of 600 Newton meter, and the portion BC is subjected to a twisting moment of 300 Newton meter, and portion CD is subjected to a twisting moment of 800 Newton meter. Now we will have to find out the angle of twist between A and D, that is angle of twist with A with respect to D is given by TL by GJ AB plus TL by GJ BC plus TL by GJ CD. That is the total angle of twist is equal to theta AB plus theta BC plus theta CD. So which gives the angle of twist A with respect to D, or angle of twist D with respect to A. Now here theta AD is equal to, here GJ is the constant throughout the shaft, because the diameter of the shaft is constant from A to D, and the material is same for the entire shaft, so that 1 by GJ is constant. Now take GJ outside, and here it is TL of AB plus TL of BC plus TL of CD. So here 1 by G is given by 28 gigapascal, so that here 28 into 10 power of 6 Newton per meter square, sorry 10 power 9, and here J is pi by 32 d power of 4, so here D is 0.054 power of 4, and here TL of AB is the torque applying on the portion AB is 600 Newton meter, and the length of the shaft, length of the distance between A and B is 2 meters, or length of the portion AB is 2 meters, and here it is 300 into 3, and it is minus 800 into 2, and this is also minus 600 into 2 plus 300 into 3 minus 800 into 2, which gives a value of 0.1105 radians. But here we need it in degrees, so just multiply with 180 by pi, which gives a value of 6.36 degrees. 6.34 degrees. So in the option, the right option is C. The drum is 500 mm as shown in the figure and it rotates at 250 rpm. Coefficient of friction is 0.25 and drum width is 80 mm. Calculate the average braking power. So here is the given diagram. So in this case, the drum rotates at 250 rpm and here is the column of length 500 mm and a 4000 Newton applying at the free at one end of this column, and here it is fulcrum. Now consider the free body diagram of this. So this is the 4000 Newton load acting at this point, and here so it is a reaction Rn is acting, and here the friction is mu Rn. And here this fulcrum axis coincides with the this axis, that is the frictional force axis, and here by taking moments about this fulcrum, we can get here moments about fulcrum. Let us say this is 0. 4000 into 500 minus Rn into 200 is equal to 0. So from this you can get here Rn is 10,000 newtons. So we know that here braking torque is given by mu into Rn into R, and the braking power is given by T into omega. So here the total power is equal to mu into Rn into R into omega, where mu is the 0.25 and Rn is 10,000, and here R is 250 mm or 0.25 meters, and omega is 2 pi n by 60. 2 pi into n is 250 by 60. So it gives a value of 16.36 kilowatts. So in the options, the right option is A. A is the right answer. Mass of M is attached to a spring whose upper end is fixed. The mass and stiffness of the spring are M and K respectively. The natural frequency of the spring mass system would be. So the given problem is a spring is fixed at one end and attached to a mass of capital M, and the spring mass is small m and stiffness is K. Here these two are in series combination, that is spring and mass. So here the total mass is m plus m, but here the equivalent mass of the spring becomes equal to m by 3, so that the natural frequency of the system is given by 1 by root 2 pi is equal to k by m plus m by 3, which is equal to 1 by 2 pi 3k by 3m plus m.